Subtopic 1.1 Moles, aka how very small and numerous atoms and molecules really are and how we can measure them out in real life. There's many ways we can count large groups of things. For example, dozens, which are 12, such as a dozen eggs, a dozen students, or a dozen sunny days, which is almost 2 weeks. And we can count by larger groups, such as 1,000, like 1,000 eggs, 256, 512, 768, 1,024, oops, too many, or 1,000 students. And even 1,000 sunny days, almost 3 years of nice weather. Assa! If we wanted to count truly large groups of things, we could use moles. A mole is a big number, 1,000, million, billion, trillion, quadrillion, quintillion, sextillion, 602 sextillion. That's enormous. If we had a mole of eggs side to side, that'd be nearly 3 light years long. If we had a mole of students, that would weigh about as much as 7 planet Earths. If we had a mole of stars, we'd have all the stars in the universe. And here is just a small portion of the Milky Way, our own home galaxy. This makes me think A, there's a lot of stars, B, the mole is a truly large number, and C, we're very tiny. Speaking of tiny, what things might be better counted in moles? How about the human brain? There's a lot of nerve cells there, but that uses only up a few of the digits of a mole. How about all the connections between all those neurons? No, not even close. The same for all the cells in the human body. By the way, if you think that picture of the human body is gross, then don't ask how we counted all the neurons. How about moles and chemistry stuff? If we had 100 milliliters of pure water, we would find about 5.5 moles of water molecules, the same number of oxygen atoms, of course, and twice that number of hydrogen atoms, of course. We'd also have about 10 times that number of protons or electrons. How about air? Take a breath. You have in your lungs a bit of nitrogen gas and some oxygen and some argon gas and some carbon dioxide, all fairly conveniently measured in moles. So here's the definition of a mole, and we know that a mole is this large, and that one carbon atom weighs 12 AMU, so we can rewrite the definition in math like this. Cancel a few units, simplify some numbers, and we get this, which is where we get Avogadro's number from. Notice the units on Avogadro's number. Or we can rewrite the expression like this, which makes it easy to do some simple chemistry problems. For example, if we had 1 mole of boron trifluoride, how much does that weigh? Well, we need to find out its relative molecular mass. If we look at the periodic table, boron is 10.8 AMU and fluorine is 19, and that adds up to 67.8 for the whole boron trifluoride molecule. 1 mole of this will be the same number in grams. How about if we go the other direction? Let's use methane. We have 16 grams. How many moles is that? We go back to the table. Hydrogen is 1 AMU, carbon is 12, so that makes 16 again. So, since it's the same number in grams in AMU, that's 1 mole. This is why chemists have defined the mole this way. It means that for 1 mole, its mass in grams is the same as the mass of the single molecule written in AMU. That's it. Thank you.